Hello everyone, we are Team 36 and our topic is View Consistent 3D Super Resolution. So what is super resolution? It's basically transforming a blurry image into a sharp and clear detailed one. And we think if we can do this in 3D, it will be very helpful in industries like game development. And there are many 2D super resolution methods, but few people have done this in 3D. But why? That's it because 3D data introduce new problems because it's costly and time consuming to process, and it's have issues like view consistency. And our mission is to make 3D object more clear and with better view consistency and efficiency. So we are trying to adopting a 3D generation method with better view consistency for 3D super resolution. Our input is like the sparse point cloud on the left, and our expected output is a more detailed 3D representation on the right. The dataset we use is called CAP3D. It's a dataset with 3D object and captions. We randomly select 46 data points from the dataset and apply furthest point sampling as the preprocessing step. One important thing to note is that we are optimizing the data and not the whole model. So how do we represent 3D shapes? Gaussian slatting is the state-of-the-art model for representing 3D representations. And we are all familiar with Gaussian in 1D and 2D. But 3D Gaussian is actually just an ellipse in a space. And we can see on the right, each point is just an Gaussian with different color and opacity. And as we zoom out, we can see the Gaussian becomes the basic building blocks for the whole detailed 3D representations. And let's go through our pipeline. We start with a sparse point cloud, and after noisy point growing and color perturbation, we get a more detailed point cloud, and we use it to initialize our 3D Gaussians. And then we render our Gaussian representation into images and add noise into it. After we feed this into a diffusion model with a prompt, we get a more clear and sharp 2D images. And then finally, we use these images to optimize our 3D models. This is an iterative process, and we do this multiple times to finally get our 3D representation. In this whole pipeline, we have two key improvements. The first one is that we use better noisy point growing and color perturbation methods. And the second one is that we use a view-consistent diffusion method. We'll introduce this one by one. In the noisy point growing and color perturbation method, we take the sparse point cloud and randomly insert point with similar colors. And we can see on the right, the sparse point cloud becomes more detailed, and this will greatly help the optimization process of the 3D Gaussian. And the second point is that the original baseline used a diffusion model, which is not view consistent. And we can see the cartoon character has a very different front view and back view. Its head becomes red. And we try to improve this with a view consistent diffusion model, which takes in not only the prompt, but also the camera angle. And with this additional information, we can get view consistent to the images and different camera angles. And we hope this can aid the optimization process of the 3D optimization. And we can show our results. The left is the sparse point cloud, which takes an input. And we can clearly show that on the right, our result is more diverse in both shape and colors. So when we compare our result with our baseline, we can see that it's more consistent with the prompt, and it's also more robust with the artifacts in the original data points. And it's also more view consistent because it generates only one face for the skull, and we can see it's more detailed in both shape and colors. Finally, we did an ablation study on the random growing stage. You can see without the random growing stage, the model doesn't have enough information to reconstruct the whole 3D representation. It gives incomplete and sparse result. But with our added random growing stage, our model can generate consistent and detailed representation no matter how many points we have at the start. But our model is also not perfect. It can sometimes suffer from hallucination problems. As you can see, the original 3D representation, the person is actually naked. But our model somehow hallucinates and put clothes on the 3D representation. And that's all for our project, and thank you for listening.